First, we'll take a look at a question from May, June 2023. This is question 12. The question starts by asking us, what is meant by recursion? Well, recursion is a process through which a function calls itself. So it is when a function or a procedure or really any subprogram is defined such that it refers back to itself. And in order to further explain what happens in recursion, you can talk about the base case and the recursion case, or the base case and the general case, where the base case is where recursion would stop and the function starts unwinding, and the general case is where the function would keep on recursing or calling itself. So the way I would write an answer to this is first by defining what is recursion. Recursion is the process through which a function or procedure is defined such that it calls itself, right? So that's the starting sentence. And then to add, a recursive function or a recursive subprogram, to keep it general, has a general case, also known as a recursive case, under which the subprogram keeps calling itself. This is referred to as winding. And it also has a base case. Which stops recursion and returns a value. This is referred to as unwinding. So yeah, hopefully this makes sense. Recursion is a process through which a function or procedure is defined such that it calls itself, and a recursion subprogram is made up of two components. Number one is winding, which is where the function calls itself through a general or recursive case. And then there's a base case where the function stops recursing and it returns a value, which is referred to as unwinding. All right, now the next part of this question says that there is a Fibonacci sequence calculation function, which essentially gives us the values of Fibonacci, right? So for those of you that don't know, it states that Fibonacci is a series of numbers formed by adding together the two preceding numbers. For example, you start off with 0 and 1. 0 and 1 are actually the base case, where for 0 and 1, you need to define that they are the beginning or starting values, because there's no way to derive 0 and 1 here, right? You need to have at least two values at the beginning before this Fibonacci sequence can begin. And I have a video dedicated to this, so please check it out. It's detailing entirely how recursion works, and I also detail how the function here can be written from scratch. So check it out. But anyway, the starting values have to be defined. And then after that, the next value 1 is formed by adding together the last two values. So 1 is a result of 0 plus 1, which is 1. 2 is a result of 1 plus 1. So you can imagine it grows exponentially of sorts. Not really exponentially, but you get the idea. It grows pretty fast, as the sequence progresses. Now here there's a function that calculates and returns the values in Fibonacci and uses recursion. Okay, so let's see how this works. Well, there were a function called fib that takes in a number as an integer, and it has an if condition that checks if the number is less than or equal to 1. So that's defining the base case, right? That's the base case. And if it's less than or equal to 1, we return the number itself, which is either 0 or 1. Otherwise, what happens? Otherwise, we encounter the recursive case or the general case, whatever you want to call it. Let's call it the general case for now. Where in the general case, which is under which recursion happens, you actually call the Fibonacci function again, right? You call the Fibonacci function again, but with the current number -1 plus the current number -2. So for example, if the number is equal to 4, we are saying that Fibonacci 4 is equal to Fibonacci 3 plus Fibonacci 2, which makes sense, right? Kind of like saying this 2 is a result of the previous one plus the one before that, right? So pretty straightforward, I hope. And it ends up returning the result at the end. Otherwise, the functions that call the functions in turn would not be able to access the resulting value. So returning is important. Otherwise, the function calls will not be able to get the return value. So very important to return. In this scenario, at least. In other scenarios, returning may or may not be mandatory, but you need to absolutely have some system in place to stop recursion in a situation where the base case is achieved. In this case, that's done by the return statement. So the goal here is not to really understand much about the implementation, but more along the lines of completing a trace table. So our goal is to now complete a trace table for the function when it is called as fib5. All right, so here's how you would implement a trace table for this kind of situation, right? Very important, so make sure that you guys pay attention. Basically, you start by visualizing what happens when you immediately call this function fib5. Well, you can imagine that the first call occurs. So I'll write call number 1 in the first row. And when the first call occurs, the function that gets called is fib5. So fib5 is the first function call that occurs in this recursive sequence. And since you call fib5, where 5 is the number that's passed in as a parameter, the number becomes 5 as well. And then you check one of these two if conditions. Is the number less than or equal to 1, or is it greater than 1? In this case, the number 5 is not less than or equal to 1, it is greater than 1. So we end up recursing. So what we do is we call fib number -1, which is in this case 5 minus 1, 4, plus fib number -2, which is 5 minus 2, 3. So the result would be fib 4 plus fib 3. So keep in mind, in recursion, you never end up evaluating the final answer in one go, right? In this case, you end up calling the fib function again. So these are referred to as intermediate results, where you don't immediately realize what the Fibonacci, what the fifth Fibonacci number is. It has to incrementally evaluate this, right? But yeah, this is the intermediate result. And right now there is no return value, because when you set the result to fib4 plus fib3, right, we end up actually calling the function again from both these function calls, such that this return statement is never achieved. You never get to this point in the program. So you're now calling the function again, but this time you have two function calls. Which one do you choose to evaluate next? You choose to evaluate the leftmost function call. So the second call would be of fib4. In fib4, what happens? In fib4, you take the number in as 4, and when fib4 happens, you check if 4 is less than or equal to 1, which is not the case, and you call fib4 minus 1 plus fib4 minus 2 again. So the result would here be fib3 plus fib2. Right? Cool. All right. Now that you're in this function call, again, you need to evaluate the leftmost statement, which is call number 3, fib3, which is number 3. And here, as you can probably guess, you're going to be running fib2 plus fib1. And then with fib2, what happens? Well, again, you need to call this again. So this is call number 4, fib 2 is what happens now, the leftmost function call out of the 2. You're now running the same function but with number 2 in the parameter. This results in fib1 plus fib0. All right. So now again here, you need to evaluate the leftmost function call first. That's this guy, which means that in call number 5, you need to run fib1, which is the Fibonacci sequence, but the first sequence number. So the number is 1 in this function call. But what happens in fib1 is interesting because here we reach the base case, right? The number 1 is less than or equal to 1, right? It is 1. So what happens is, for the first time, we set result to number, right? So the result is actually 1. And this would then mean that we can directly return result without having to call the function again. So we end up at a situation where the recursive function fib now starts to unwind. And the return value would therefore be 1 as well. But then keep in mind, we got to this point because we evaluated fib1. But there's still a fib0 left from the previous function call left to evaluate, right? So now we need to evaluate that. Keep in mind, we cannot half evaluate return statements. We need to evaluate the full thing. So we need to call the function again, but this time with fib0, where the number is 0 that's passed in. Here the result would of course be the same. It'll be, the result is whatever the number is, which is 0, and you return 0. So now fib1 has been evaluated and fib0 has been evaluated, which means that call number 4 can be completed. We know what fib1 and fib0 is, which means that you can now mention that you're back in call number 4. So keep in mind, we can rewrite the same call numbers to indicate that we are now unwinding. So up until this point, we were winding, which is going into function calls. And from this point on, we are going to start unwinding, which is where we start returning. So now we are back at function call 4. Having evaluated what fib1 and fib0 is, we can now rewrite the function call that we were previously in. Maybe I'll put this in separate colors so it's easy to see. So these are all the winding calls. Starting now, we are now going to begin the unwinding calls. All right. So the unwinding calls would begin with call number 4, which is back to what we were at before, which is fib2, where the number is of course 2, but now we can finally evaluate what fib1 and fib0 is, because as a result of these two function calls, we know that fib1 is 1 and fib0 is 0, which means that 1 plus 0 can finally be evaluated, resulting in a number 1, which is 1 plus 0 is 1, and then that gets returned. All right, cool. And then now you need to ask yourself, what called fib2? Well, the function call that was responsible for calling fib2 is fib3, right? We called fib2 here, which means you need to now return that result back to fib3, right? Which means that we are back in call number 3 now, where we were previously calling fib3, the number 3, where now that 1 plus 0 or fib1 plus fib0 was returned with a value of 1, we can now take that answer as the answer to fib2, which would be 1 again. Now, we also know what the answer to fib1 is. Fib1's answer is 1, which means that this would then evaluate to 1 plus 1, 2. So hopefully you guys see the pattern. Now we repeat this for the function call before fib3, which is fib4, which is function call 2, fib4, for the number 4, where now the result is going to be whatever fib3 returned plus fib2, which is 2 plus 1. That's going to be 3. And now we are back to function call number 1. We're back at the topmost function call, where we are now calling fib5, where here the number is 5. And we take these two results, fib4 plus fib3, which is 3 plus 2. And voila, that's it. That completes the trace table for this Fibonacci recursive function. So keep this in mind. This is the general strategy to approach when it comes to filling up recursive trace tables. If you have any questions, let me know in the comments. All right. Take a quick minute to make sure that you digest all of this. All right, perfect. Let's now move on into the next question, which is a pseudocode question. All right, what does it say? This is from the May, June 2023 paper, question number 11. The pseudocode below represents a queue abstract data structure with procedures for initialization and to add new items. Apparently, it's incomplete. Okay, so let's quickly go through the pseudocode. They've defined a constant called max length. They've declared the front pointer and rear pointer. Whenever you see the front pointer and rear pointer, remind yourself that the front pointer is what changes or what's responsible when we dequeue items. Because keep in mind, the front pointer, basically, it is from the front of a queue that we dequeue, right? People remove themselves from the front of a supermarket queue, for instance. So similarly, a queue must remove from the front. It's the front pointer that's responsible for dequeuing. And it's the rear pointer that's responsible for on-queuing. All right, cool. Then we've declared the length. Oh, okay. So the fact that the length exists here should probably mean that this is a circular queue, right? So that's cool. This seems to be a circular queue then. Because if you recall, in a linear queue, we don't really need to maintain the length because we don't really need to know whether there's space left at the front or the back when we go back to the beginning. But here, since we maintain a length variable to tell us whether there is space left in the queue, that probably means that this is a circular queue. But yeah, then we declare the queue itself, which is an array with a lower bound of 0. This is quite important. There's a lower bound of 0, which sometimes confuses most of us because usually we would expect pseudocode to start counting arrays at 1. But here, the lower bound is 0. And then there's a max length of max length minus 1. That's the upper bound. So here, the array indices would therefore be from 0 to 49 because we start at 50, right? Or at least the max length is 50. So this is very similar to how arrays work in Python. So they've confused us a bit, but hopefully it wasn't too confusing. All right, so we need to fill in some blanks, but let's not worry about that right now. The first question tells us to study the pseudocode and insert the identifiers to complete this table. All right, so seems like we went through all the identifiers. We went through all the constants and variables. Let's now figure out what identifiers match these descriptions. Which identifier is an array to store the contents of the queue? Well, that's the queue itself. That's capital Q, U, E, U, E. All right, next up. Which variable points to the last item of the queue? Well, the last item of the queue should be at the rear, which is to say that it is a rear pointer. Yep, rear pointer. And right off the bat, I can see that the last row expects us to tell us the identifier for pointing to the first item, which makes sense. It's the opposite of the rear pointer. That's the front pointer. So let me just fill that in right away. And then which variable tells us or indicates the number of items in the queue? Okay, that's the length, right? The number of items left in the queue is the length. All right, cool. So that's that. Finished. Okay, question 5 asks us to complete the given pseudocode. All right, well, let's think about this. The first missing pseudocode lines are for the initialization phase. Well, if you guys remember, when you initialize a queue, we need to initialize the front pointer, rear pointer, and length. Now, there's already some statement that has to be set to 0 here. And if you think about it, it's probably length that has to be set to 0 to begin with. So let me just fill it in here to indicate that at the beginning of the queue, there's nothing in the queue, so the length is 0. Now, the next obvious variable that's left to initialize is probably rear pointer, right? Rear pointer. But the question is, I don't really know as of now what to initialize rear pointer to. So I'm just going to leave that as a blank because when I go through the on queue process, hopefully I'll get some more insight as to how or what rear pointer should be initialized to. So I'm just going to leave it at that, and let's see if the onQueue operation would give us some insight as to how rear pointer should work. Right, so let's look at the onQueue procedure. Onqueuing is the process through which we add a new item to the queue, as the comment itself tells us. But one more important thing to keep in mind is that the onQueue operation is what determines uh, the rear pointer's position, right? So if you recall, I mentioned at the top, the rear pointer is the pointer that's involved in onQueuing, right? So let's forget about the if condition for now. What happens inside this procedure? We start off by setting rear pointer to something. Well, what exactly happens when you onQueue, guys? Well, if you recall, how onQueuing works is that you have to increment your rear pointer, and then to that position, you add the new item, right? Which means that this statement is probably rear pointer is rear pointer plus 1. So you need to increment rear pointer, and then into that position, we need to insert the value. Now, the value insertion probably happens here. That's this line here. So let me just write that out. Basically, we take the new item and we insert it to the rear pointer index of the queue array. So we would say queue rear pointer arrow new item. And just to double check, new item is a string. Our queue is also made up of strings, so no need to do any type conversion. That's cool. And now, if you were to look at this statement here, that should give us some insight as to what rear pointer should begin as. Now, if inserting the first item would first result in the rear pointer being incremented, and keep in mind the first index of our array is 0, right? So which means that we need to start at a certain rear pointer value such that incrementing it would get us to 0, because that's the first array index. So if you then think back, if incrementing a value by 1 gets you to 0, the original value should be 0 minus 1, which is to say that rear pointer should therefore initialize as minus 1, isn't it? There you go. So that sentence or that pseudocode line would have given us some insight as to what the rear pointer starting value is. So yeah, rear pointer starts at minus 1. It gets incremented, which then results in the rear pointer becoming 0. And it is there that we insert the first item, which makes a lot of sense. And then if you look at this if condition that I ignored earlier, this if condition says if rear pointer is greater than max length minus 1, we return rear pointer to 0. So this is that circular behavior programmed in. All right, cool. Now for the last if condition. This if condition, as you probably recall, is the if condition for checking if the queue is full, right? Because if you recall how we wrote queue codes or queue implementations in class, we need to always check if our queue is full before we actually end up adding anything to the queue. So how do we check if the queue is full? Well, that's where the length variable comes into play. Basically, if the length variable is equal to max length, right, then we know that our queue is full, right? But here we need to write the opposite condition, because this if condition is what happens when the queue is not full, right? So this has to be updated to say this is checking if the queue is not full. So if the queue is not full, we would do this stuff, which means that this if condition should probably be something along the lines of if length is not equal to, but less than max length, which is the constant 50. And voila, that is the full circular queue implementation in pseudocode, at least the initialize and the onQueue procedure. Not bad, right? Hopefully that's all clear. If you have any questions, again, let me know. But now we'll look at part B. Explain the reasons why a queue ADT works better than a stack ADT for organizing print jobs. Okay, well, this is a bit of a curveball kind of question, but it's pretty easy if you think about it. How does a printer work? A printer prints documents, but if you think about how print jobs are organized, what that means is if you are trying to print multiple documents at a time, and if you send them all to the printer has to print out the first document you sent first, which is kind of similar to how a queue operates, right? A queue operates under the first in, first out basis. So that's all they expect you to write here, right? So you can say print jobs are uh, handled in the order they are received. That is to say that when you send 5 print jobs, whichever print job you send first is the first thing that that the printer should handle, right? So you first accept that that is the order that the print job should work under, and then you say that the queue is what supports this order because a queue operates under the first in, first out basis. Since a queue operates under the FIFO basis, the first job, or I would just say document sent to the printer will be the first document to be printed. Right now, why would the stack not be suitable here? If a stack were used instead, the first document sent to the printer will be the last document to be printed. This is because a stack operates under the first in, last out, or last in, first out basis. There you go. So you get 3 marks for stating the fact that a printer prints stuff in the order they are received, acknowledging that a queue is the best scenario or the best ADT for that job, and proving that a stack is not the best guy for that job by talking about the converse. All right, so that's that. So a typical question you get under chapter 19. Take a minute to digest all of this and let me know if you have any questions. All right, now we are on to another question, again for the programming chapter, which is now about file handling. This is from the May June 2023 paper 3.3, question number 10. Let's read. A pseudocode algorithm shown, or the pseudocode algorithm shown, copies active account text file. Oh, sorry, I didn't read this correctly. The pseudocode algorithm shown copies an active accounts text file called activefile.txt to an archive accounts text file called archivefile.txt, one line at a time. Okay, so it's kind of like a backup program. Any blank line found in the active accounts text file are replaced with the words account not present. And this is in the archive accounts text file. So, okay, we're supposed to complete the following file handling pseudocode to, I guess, implement this logic. Okay, well, let's see. We first declare this variable called account, which is probably the line that is being read. As you can see here, this is the line that we are reading from the active file.txt, which is yet to be copied to archive file.txt. So that account variable is the line that we are reading from the file. And then seems like Cambridge has opened the archive file.txt for us, but they haven't opened the active file.txt for us. So let's do that. We need to say open file within quotations active file.txt. Make sure to include the extension. For this time, we'll be reading. Keep in mind, we are reading. So we need to say for read. All right. Cool. So now both files are opened. Now we need to go through the active file line by line until we reach the end of the active file. So that's done using the EOF command. When you say while not EOF, within quotation active file.txt. So you always say EOF on the file that we are reading from, not the one that we are writing to. So it's while not end of file, active file.txt. We read the active file line into the variable account, and then we check if that line number or if that line, sorry, is blank, which is to see if that's equal to an empty string. If it's equal to an empty string, what does the question expect us to do? Any empty strings or any blank lines are replaced in the archive file with the words account not present. So let's write that in. Write file archive file.txt, comma, account not present. But if the account is not a blank line, then we can write the account itself to the archive file. And then finally, just as much as we close the archive file, we need to also close the active file. So close file, active file.txt. Cool. So this is a very simple file handling code. Please make sure that you guys understand all the file handling commands you have in the syllabus. For standard text files, you have your read file and write file commands. For random files, we need to use the get record and put record commands. And this is in addition to the standard open file, close file. Keep in mind, when you open files, there are 4 different modes you can use. You can open a file for reading, writing, appending, as well as random, which is when you get to use these 2 commands, right? And then of course you have close file as well, like I said. But yeah, keep these commands in mind. Make sure that you go through questions to understand how these commands work.